Good afternoon again. It's my pleasure to introduce a really exciting, what Fernando called a rock star speaker. Okay, so I start the tradition here first. Happy New Year to you. This is a New Year hat. I know many of you have already had your New Year's, but there are still many people who are waiting for their own ethnic New Year. So there's a purpose of this. Okay, first of all, I believe Paul is really a good, exciting speaker. So I want to excite you. Second of all, during the question and answer session, if you ask a question, you're going to get one of these things or maybe a toy for Happy New Year celebration. So remember that. Well, I think I'm going to leave it on for some time. It's my pleasure to introduce Paul Sajda, who is a professor of biomedical engineering, electrical engineering, and radiology at Columbia University. He's director of the Laboratory for Intelligent Imaging and Neural Computing and co-director of Columbia's Center for Neural Engineering and Computation. His research focuses on neuroengineering, neuroimaging, computational neural modeling, and machine learning applied to the study of rapid decision-making in the human brain. Prior to Columbia, Paul was the head of the Adaptive Image and Signal Processing Group at the David Sarnoff Research Center in Princeton, New Jersey. He received his BS in EE from MIT, his MS and PhD in bioengineering from UPenn. He's a recipient of the NSF Career Award, the Sarnoff Technical Achievement Award, and he's a fellow of IEEE and the American Institute of Medical and Biological Engineering. He is the current editor-in-chief for the IEEE Transactions in Neurosystems and Rehabilitation Engineering, and he's the chair of the IEEE Brain Initiative, where I met Paul. It's a real honor. He's founder and co-founder of several neurotechnology startup companies. One of them actually we're looking for showing on the CES floor next year. So please join me welcoming Paul to speak on integrating BCI technology with AR and VR.
I told Narissa I would put this on at least for a minute or two. Let's make sure this all...
You decide when you want to take it.
Yeah, So I'll dip my, or raise my cap to Narissa and thank her for this invitation. I also want to thank her. Like she said, I'm the chair of the IEEE Brain Initiative, which is a IEEE-wide initiative focused on looking at how IEEE, as the professional society for engineers, can make an impact in worldwide brain initiatives that are multi-billion-dollar initiatives going on today. Narissa is representing the Consumer Electronics Society in a very energetic and quite impactful way. So I thank her for her volunteer work there. What I want to do today is talk a little bit about some work that we've been doing looking at how brain-computer interfaces and that technology can be integrated within the world of augmented reality and virtual reality. And so anybody that attended CES knows that virtual reality, augmented reality was basically everywhere. In fact, I was surprised. I spent a lot of time at the auto parts of the CES exhibits, and almost all of the major auto companies and OEMs were using virtual reality as the main display and interaction environment for giving people an idea of how autonomous vehicles might operate. So even though there's been some some limited success and maybe some big-time failure in AR and VR over the past decade or so. I think there's a lot of agreement that AR and VR are kind of on the cusp of really taking off. And so one question that naturally arises is you have this very cool technology that's starting to potentially become something of consumer grade, or at least having implications in the world of consumer electronics. What's other cool technology you can include in it? And I think one issue with VR and AR is this idea of how do we think about interacting in these types of environments. So brain-computer interface technology is another kind of hotbed technology area that there's been a lot of promise about and a lot of claims. Just for those of you that aren't really familiar with brain-computer interfaces or BCI, there's huge research efforts and some relatively small commercial efforts to look at how we can record from the brain, either invasively or non-invasively, signals that represent intent, cognitive state, things that are less easily captured through behavioral measures or other types of physiological measures, and use that as essentially as a channel, an information channel to a computer system. And so there are efforts ranging from developing new types of interfaces for individuals with severe neurodegenerative diseases such as Lou Gehrig's disease or ALS, or major types of trauma. And for instance, there's an example here of an individual. This woman is controlling a robotic prosthesis by modulating activity in her motor cortex through implanted electrodes. So that little box on top of her head is essentially a set of electronics and a stabilization platform, but those electrodes are implanted in her brain. So she had nerve surgery. And clearly when somebody has very limited capabilities for movement or for communicating, these types of channels that can be formed through BCI potentially have a lot of value for improving their quality of life. Now, there are also many examples of non-invasive systems that are using what's called typically EEG, electroencephalography, to record data from the brain. This is not requiring any surgery at all. It's basically measuring electrical potentials at the scalp and using that information to, let's say, control. So to control a wheelchair by decoding information that's related to an individual thinking about moving left or right, or establishing a communication channel for somebody who can't, let's say, type or move. And so these types of systems have started to get integrated into VR, AR environments. And it's still at a very early stage of integration. So there's lots of these proof of concepts that are typically being developed within the academic world, but because there's kind of a lot of excitement, there's this tendency to want to bring it into the commercial world as fast as possible. And kind of the applications that have been looked at range from driving to obviously gaming and also rehabilitation. And there's a major focus on direct control. So this notion that I want to be able to move in an environment by just thinking, okay? Now, what I'm going to argue in at least the next few slides is that that might not be the best, at least near-term use of BCI for AR and VR. And that's because, quite honestly, most AR and VR, at least in the consumer world, we can move naturally joysticks with our hands, and we can, move our eyes rather easily. And so this notion of trying to do direct control tends to be one that can be problematic, because I'm also going to talk about that these types of signals that we're measuring from the brain are very noisy. So they're essentially extremely low bandwidth channels we're talking about, maybe on the order of a bit per second. So trying to supplant something like movement of joysticks and things that have orders of magnitude higher communication rates with this very low bandwidth channel might not make a lot of sense, particularly in the consumer world when people don't necessarily have any type of challenge in terms of neurorehabilitative or disease to their nervous system. So current challenges in trying to move this concept forward, an integrated BCI and AR/VR system, there's the idea of integrated hardware and sensing platform. So what I showed here are these people wearing these caps with these electrodes on. Doesn't look very consumer electronic friendly. But I think that in many ways is an engineering problem that that's going to be solved, okay? So there's going to be a solution, and we're already seeing things like these electrodes that typically require different types of gel. They're called wet electrodes, can eventually become dry electrodes. In the case of AR and VR, if you're willing to wear a system, a rig, there's ways to kind of implant or integrate those sensors within that hardware. So that's a challenge that's there, but I think it's a challenge that's very much engineering. And that's also related to usability and the design factor. I think once that engineering is solved together with the designers, the human factors people, we can imagine kind of integrated systems, particularly in the AR, VR world, which consumers would find usable. The signal quality is a big challenge. As I mentioned, we're dealing with a rather low SNR signal. And no matter how, if we're going to use, basically, if we're not willing to have brain surgery, which I personally am not, and we want a consumer-grade system, we're stuck with that signal to noise, right? So in some sense, we can do fancy types of machine learning and adaptive signal processing, which we do, but that's the signal quality that we're going to get. So really the big challenge is how are we going to potentially use these types of signals in a way where we can show that having BCI adds some kind of value to the AR, VR experience. And like I said before, I claim that that's not in direct control. I think that in direct control, everything that we've seen so far, that type of integration results in rather frustrated users, and they all want to go back to just moving things with joysticks or with leap interfaces and things like that. So what I'm going to propose is that, instead, what we want to do is use BCI to opportunistically sense cognitive state of individuals and then use that to label their environments. Okay, so I'm going to give an example of that, and then I'm going to talk about another case of, if I have time, where we're using signals in a neurofeedback mode to also control an environment by regulating the state, the cognitive state of the individual. So as an example, this is a city taken from a walk down New York, a street in New York. This could be in Las Vegas, we're all visiting. And you know that as you're walking down the street, right, you have all these little thoughts, right? So you see things that are of interest, you kind of orient to them, you take a look, you're like, wow, that's kind of, I'm getting hungry. I saw that's a cool car. Later on, you'll see something and it'll be like, well, do I recognize that person? These are things that are just kind of going off in our head. And the world of neuroimaging, BCI, there's a lot of hype about our ability to read our thoughts, right? But I can tell you 100% that we are nowhere near understanding the brain to decode the specificity that I'm showing here in terms of these little fleeting thoughts that we have. But what we are capable of is detecting how we orient our attention to things in the world. Okay, so and I'm going to show you a little bit about the underlying biology and physiology of that in a moment. But the notion is, what could we do with this little piece of information that doesn't represent what's in the bubble, but just that I oriented to that at that particular time? So imagine a situation where I have Mr. Stick Figure, and Mr. Stick Figure has got a non-invasive brain-computer interface on, and they're somewhere in the world. So Mr. Stick Figure also they're wearing, let's say, this is an augmented reality scenario. They have, in addition, all the usual electronics that we have. They got their cell phone, it's got GPS integrated. The augmented reality cap has you know, some kind of camera system, maybe two-way camera, eye tracking, all the gadgets. No neurosurgery required so far. And there's an event, and the event is something in the world that has oriented us. And through our brain-computer interface, a signal that we detect non-invasively through the brain, this EEG brain cap, the event happens, and what do? Well, the camera is embedded in our AR system. Take a picture that ties that to where we are in the world. So a little bit about the background of the signal that we're going to detect. So the other thing I want to kind of make clear is, once again, back to the idea of BCI hype, and I'm going to editorialize a little bit. But you'll see a lot of companies and even some academics where there's a lot of claim on what they're measuring and whether or not it's truly a BCI. So for instance, I could put on a certain type of cap and I could get a signal that moves up and down, and it might have nothing to do with the brain in terms of a direct measurement of what's happening in the brain. It could be because I'm measuring an effect due to my eye movement. So there are electrical signals that are due to the fact that the eye poles actually are, the eyes are dipoles and electrical dipoles, and you can measure that through contact with the skin, or EMG. So one of the things that we want to always show is that, is there some value in the actual neural signal? And what value does that have over additional physiological signals that might be easier to measure? So the type of neural signal that we're going to leverage is the target response. And so this is a response that's been known for years, actually decades, and it was discovered in very simple academic labs where you have a paradigm where you have one type of object flashed and then a target object flashed. And the question is there a difference in the response between the target object and these distractors? And what physiologists found was that there's a response. It's typically referred to as a P300. It's a deflection in the EEG signal that occurs about 300 milliseconds after that red target occurs, and it's a positive deflection in the electrical potential. And it has a certain topology across the head. That's what you see in that little heat map, that circled heat map, which represents looking at the EEG from the top of the head. And it's well characterized. The problem is that for really decades, it's focused on these very simple stimuli in very controlled conditions, and used relatively few number of these EEG channels to measure the response. So when you look at these curves and you see these differences between the distractor and the target condition, you might say, wait, that looks like a high SNR signal. Well, this is averaged over hundreds of trials. So seeing that red dot hundreds of times, clearly not something useful if we're thinking about building a channel for transmitting information, having to wait that long to decode the different activity. So in my lab in the mid 2000s, we looked at more complicated stimuli, those that were natural images, and looked at this same response by basically using machine learning to integrate across space and time. And having the stimuli being more complicated. And we found that we were able to record the data and decode on a single trial basis. So on just basically one trial at a time, information related to whether there was an orienting or a target response to the image of interest in that particular scenario. Now what we're talking about in kind of the target response 3.0 is we have even a more complicated condition. So instead of having a single type of stimulus that's very simple, or a natural stimulus but it's moving very quickly so we can't move our eyes too much, we're actually in an immersive 3D environment that's dynamic. We're moving our eyes. That potentially causes lots of different confounds that we have to deal with. But ultimately what we're doing is we're going to use VR as our platform to test this idea of using this target response to label the world. I'm going to go into the experiment in a moment. First, one little simple I got to show a brain, right, at some point, just to give you an idea of, we know where this target response comes from. So this is a brain. This is actually half of a brain, where this part, if you can see here, this is the front of the brain, this is the back of the brain, this is the part of the spinal cord, and this is the cerebellum, midbrain here. So when we look at this, when we have this targeting response, it's this orienting I talked about. So what happens in your brain is something in the world that has value, is of interest, potentially is threatening. That causes a shift in your attention. And your prefrontal cortex, that part that's labeled there, anterior cingulate, is all about creating models of the world, learning models of the world, and when those predictions of a given model are wrong, tries to orient and switch a model. So the anterior cingulate, or the prefrontal cortex, is very much related to this orienting effect. It's also highly coupled to this part deep in the brain, in the midbrain and the parts of the upper spinal cord, called the locus coeruleus. This is actually a really tiny area in the brain, but it is involved in an arousal circuit. So when you change your or reorient your response, your arousal level switches. So you get a change that happens in the brain. There's a loop here that is involved with linking this circuit, but then the arousal also changes the rest of the physiology in your body. So if we want to measure this target response, if that's going to be our important signal that we measure, we want to measure activity from these two areas, these two regions in the brain. Well, if these are all the little electrodes, these little gray things that we have on our head, they're actually pretty good at measuring the activity in the anterior cingulate. Anterior cingulate is a pretty big chunk of brain, and it's pretty close to these electrodes. These electrodes cannot measure what's happening in this little locus coeruleus. Not only is that too deep, but the number of neurons or cells there is tiny. So the electrical potential is tiny, even if it was at the surface. Now what's interesting, though, is we can actually measure what's happening with the pupil, okay? And so the pupil, turns out, and the neural circuitry involved with controlling your pupillary response is right next to this area, this locus coeruleus area. And what you see here are two curves, one that represents how the pupil dilates, and the other, the activity in this little area, in locus coeruleus. And so the idea is that instead of thinking about measuring all of this signal within the context of just these EEG sensors, what we want to do is we want to fuse multiple different signals that give us kind of a picture of a facet of the orienting response. So we're going to look at not just the EEG, we're going to look at the pupillary response, we're actually going to look at how the eyes move and their fixation duration, and integrate this into a hybrid brain-computer interface. So that's another key thing for making some of these systems consumer grade, is the need to integrate physiology that is brain and non-brain together with other types of input to provide value to the consumer. So here's an example of our experiment for labeling the world. So we create a virtual reality environment where an individual has to move through the environment, and they have one control signal directly. So they actually are just told to slow down. So they press a key on the keyboard when this truck in front of them brakes. At the same time, they're told to look out for certain types of objects in these alleyways. You might see them as they're going by, and they're told beforehand either to select a category on their own, or they're told to of a given category to look at. And what they're going to do is they're not going to respond when they see that category. All we're going to do is decode the activity that's coming from their brain, and we're going to use that as an extra channel in addition to what, I mean, they have their primary task of pressing the button to slow down, but we're going to try to decode the secondary channel to label the world of other objects that might be of similar nature and of interest to them. So first, to look at the physiological responses. The over here, you can see these are the same 3 electrodes that I showed before in the target response 1.0. These differentiate targets and distractors. In this particular case, objects of interest they oriented to versus objects that they didn't orient to in the environment. And one thing you can notice right away is there's a difference in the magnitude in the laboratory experiment, which is in the thin curves, versus the more immersive AR experiment. But that's okay because we've learned how to use machine learning to integrate across the time and space to improve that overall SNR. We've also learned how to integrate and fuse the information we get from the pupillary response. So these are the differences in the pupil dilation for the target and non-target objects in the world, and also the fixation or the dwell time. And so using, like I said, machine learning, I'm not going to get into the details of it, but the idea is that we fuse at each individual level information to detect these orienting events. And we fuse across space in the EEG, but also time and modality across the different sensors. So when I say sensors, I mean we've got the EEG here. That's basically that signal is done at about half a second to a second after the orienting event happens. We also have the pupillary response, which is much slower. You can see that that is a slower, much more of a low-pass phenomenon, but does have information that can be integrated with the EEG to create this hybrid brain-computer interface, as well as the fixation dwell time. So I'm not going to get into lots of results, mostly fairly high level, but one thing to show is, so what's the use of this EEG information, right? So clearly putting the cap on is a pain in the neck. So what value does it bring? And so this is results across 10 subjects who are in this environment. We're looking to see how good is the machine learning decoder for detecting these orienting events as a function of the different input modalities, whether it's just using the EEG, whether it's just using the pupil dilation, the dwell time, or all 3 integrated. So, and these are actually ordered by, from the best subject in terms of their EEG or EEG decoding to the worst, from best to worst. And what you can see is that first that the hybrid technique, the one that integrates information, rides on top of the envelope of all 3. So that's good. We're actually fusing information in an efficient way. But also what you see is there's variability across individuals. Some individuals have really good EEG that's very that has a relatively high SNR and results in good decoding performance, and in fact is the best modality for decoding relative to the other 2. While others, for instance, subject number 10 has very poor EEG, but, and the other 2 modalities, the ocular information from the pupil and the dwell time are more important. So perhaps the biggest finding here is that the use of the brain signal provides robustness across different measures. It also helps to amplify the overall performance. So if there are critical performance measures, critical boundaries you have to accept to get adoption of, let's say, a given device, it might be extremely important. All right, so now we have this signal that represents I oriented to something in my virtual environment. How do I use this? So I said that we're going to use this to opportunistically sense and label the world. So I have these labels that are coming out that represent whether I'm orienting or not. They're now going to, these labels are going to be ingested into a learning-based computer vision system to inform the computer vision of where in the environment things of interest might lie. So the type of computer vision we're going to look at is one based, it's a semi-supervised approach that's based on a graph-based construct. The details don't matter. What matters here is to think about the paradigm a bit. So imagine I have, these are 6 different objects in the environment. So you can even think about these are spatially distributed across our environment. And we build a model of these objects and their relationship just based on their visual features. So we can represent that in a graph, right? So these sailboat things, the sailboat images, those are of a stronger connection because they have visual features that are very similar in that computer vision space. Now, we as a user in the environment, in the virtual environment, can explore a piece of this space. We can just explore this part of the space that's in gray, and as we go through that space and move through it, we orient at two locations, okay? We orient at the two sailboat locations. So that information, we know nothing about from the brain signal what was there, just that we oriented. However, that information can be used as a label and said, well, what was ever there at those two locations we looked at is tied to, based on the visual features, to another sailboat outside the environment we saw. So if we wanted to recommend to the individual another place to look at, to investigate, we would tell them to go to the left, to that sailboat, and not to the right. Right? So this is a very simple idea. There's lots of machine learning that's under it that allows us to do this in a robust way, but I'm not going to be able to go into that right now. There's details in the papers that are referenced. All right, so here's an example of the whole thing in operation. So we built this environment within Unity. Person is immersed in it through Oculus VR that actually has eye tracking embedded, they're fully instrumented with EEG. And we start by having them basically move around through a part of the environment. So some of the regions that they can move around in are in gray. That information is then used. We're recording EEG and detecting waypoints or locations that, based on their orienting, are likely to have an object of interest. That information is propagated through the computer vision system, so through that labeling concept and throughout the entire network, which is represented in space. And then some kind of path planning algorithm is applied so that the user then can go through the rest of the environment in an efficient way and find other regions that they hadn't explored that potentially would be of interest to them. And so here's just a simple example. We've taken away the car to make it a little bit easier to see. If you can see here, there are these little red dots. So the red dots are locations of objects of interest that are similar to what the user was interested in, but they never saw before in the initial gray areas that they moved through. Anything with a red X is something that they saw, so it's a piece of like training data. So you can see that with relatively little training, we get a pretty efficient path that goes through and more or less tags and takes the individual across a route that exposes them to really a substantial fraction of the objects of interest. So, so how does this kind of relate back to my initial slide? Well, when we talk about the future or a potential future for AR system, or which has BCI as part of it, we can think about it as essentially a recommender system in real time that doesn't require us to make overt behavioral responses. So for instance, I can orient to something, the information is immediately characterized by local object recognition as well as textual information and information that might be relevant to me in terms of making an immediate decision can be pushed down locally. Now, this is kind of where we're going next in terms of showing proof of concept, but there's a big caveat here, or at least a big buyer beware. I was in a really good IEEE standards sponsored panel just before this, and all of these types of new types of HCI, particularly when you're thinking about the brain involved, there are huge issues that we all have to think about in terms of ethics and how we think about this type of interface in the long term. So within the IEEE Brain Initiative community, we're actively developing kind of strategies for this, both within the community as well as more broadly across brain initiatives worldwide. But you know, what's pretty clear is, though this technology is cool, and we're starting to get the pieces up so that we could potentially enable some of this, there's all the potential implications of, if we could monitor and start to build models of what users find interesting, how could we potentially overuse that or use that in nefarious ways? Okay, so I have a little bit more time, so I just want to talk about one other application, an area that we're using AR and VR for. And with respect to BCI, so one thing we can do is really look at developing new types of systems using AR and VR, because in that example, I have perfect knowledge of the world. I build the VR system, so we know where things are in the world. We can do a lot of kind of experimental testing, which could ultimately be translated into the AR experience, or maybe could be put into a VR-only experience. But another reason to use BCI and VR is to, you know, certain experiences in the real world you don't want to experience, but you want to test how people deal with those experiences, and whether certain types of mitigation are useful in improving their performance and or just saving their lives. So one area that we've looked at integrating BCI and VR is for what's called pilot-induced oscillations. So this is an interesting phenomenon, and I'm actually going to show you a video here. So a pilot-induced oscillation is one, you see this plane, and this plane crashes. And this is a fighter plane. It happens actually in all types of aircraft. And it's a result of a change in the cognitive state of the pilot. And these are very, you know, well-trained pilots, as a function of a failure boundary. So typically happens, let's say, when they're trying to land, or if they have to maintain a certain airspeed. And it's not a simple feedback kind of control loop problem. It's actually a change in how the pilot views how they should operate the plane. So there's a cognitive component to this. And it happens in piloting, but it turns out it happens in lots of different scenarios. So for instance, if I told you to walk across, let's say, a plank here that's on the floor, 6 inches wide, and I put a little piece of chalk on the back, and I timed how fast you could do that and whether you kind of tipped off the plank. Chalk on the back is going to cause them to oscillate between the boundaries. In some respects, what they start to do is, if there's a critical boundary, they start to pay too much attention to it, and it changes their level of arousal, and then their model of how they should actually do the task changes, and it changes in a bad way. So what we've been trying to do is look at ways in which we could potentially use something like BCI to provide feedback to an operator, in this case a pilot, to mitigate this type of essentially arousal change, and therefore mitigate changes in how they operate the aircraft. So the interesting thing is this notion of arousal and performance has been known for over a century in a classic Yerkes-Dodson relationship, which says that as your arousal gets higher and higher, your performance on a task tends to go down, okay? So ways in which we can dynamically change the arousal state of an individual to get them in that performance sweet spot has broad implications, not just for pilots, but others, as I mentioned. Now, you can't just tell somebody, stop being aroused, right? I mean, it's not like you can say, everything's going to be fine, or we've even done experiments where we try to change the control stick of the individual as they're trying to fly the plane. They end up ripping the control stick out. It just makes them more nervous. So another question is how you provide this feedback to the individual based on their brain state. Okay, so just once again to touch on the basis for this, and the reason I want to mention it is we're looking at the same kind of circuit that I talked about before in this this targeting response is also the basis for how arousal affects our performance in a given task. And once again, I've said that this part of prefrontal cortex, this anterior cingulate, is basically all about what model we use based on what we're doing in the world. And so when arousal increases, that typically generates what's called the flight or fight response, right? And you go into this mode of, instead of really taking into account what you're getting from your sensory world, you just ignore it and you just run. Or you do something dramatic, like you pull the stick to the left or to the right. So this same type of signals that we were using in the previous case, we're using in this case too. So we're actually using a hybrid BCI, but processing them with our machine learning in a little bit different way. Okay, so once again, the idea is to use this biometric that we're getting from the EEG and the eye movement information to switch in kind of a unobtrusive way the arousal state and improve the performance of the individual. So obviously we're not going to send people out in planes to do this. We have to first start when they're in a virtual environment. There's a big difference in our ability to do these experiments and what we find when we do it, let's say, just on a regular display versus in a virtual environment. The level of your heart rate, your galvanic skin response, all these measures of arousal are way higher and much more realistic when you're in the VR experience. So we measure and we sense the brain signals through electroencephalography, the pupil size as before. We also measure things like the EMG and the heart rate, respiration, so forth. And we integrate all these in the same kind of concept as I mentioned in the previous example. So the hypothesis and what we build is a closed loop feedback system where what we're going to feed back to the individual is a low rate, heart rate, that is that should calm them down. So a very low beat heart rate that first, if their arousal is low, they can barely hear it, so they ignore it. But as we start to decoding that this arousal and this what we would call cognitive inflexibility starts to ramp up, we increase the volume of that heart rate. And what this does is takes advantage of a known fact that we naturally entrain to our heart rates. And the heart rate, if we can change the heart rate, that changes our overall arousal systemically, which then affects what happens in that little brain region, the locus coeruleus, which then affects what happens in that anterior cingulate area that I talked about that is going to cause us either to go back and forth and shift or to chill out and take the appropriate action. And so we do this all within the context of a task that has they have to basically a flight simulation task where the operator has to move through these glide paths in different ways, and the glide paths become more or less difficult as a function of time. And here's just a little video showing the person here. There's a little bar here, which is the output of the hybrid BCI decoder. They don't see that. Turns out if they see that, they get even more stressed out, right? Because they see this red bar going up. So dampening the stick or giving them visual feedback is the wrong way to interact with them within this virtual environment. Instead, the right way to interact is through providing this heart rate. It's almost like this meditative experience. You start to hear it and you naturally kind of reduce your overall arousal state. So does this work, right? And so what we found is, and this is for 10 subjects, these are all novices, so we're now currently also doing these with pilots. And we find that we get significant improvement in how long they can fly before having a catastrophic event if we compare the feedback we give them either through no feedback, so just silence, so they don't get anything, a sham feedback, which is a combination of the real brain state together with some modeled random state, and the true feedback, right? So you get these changes in time, in terms of z-scored time of flight that are highly significant. And so We've been working with DARPA and the Air Force Research Test Facility to look at this with different types of individuals, because even though this works, let's say, on the novice, the gamer type, question is, how does this actually affect a pilot that might have a different way in which they interact and deal with these types of scenarios? All right, so in summary, so these are just two examples of how we've been integrating hybrid brain-computer interfaces with VR and AR. And I think that there's clearly lots of examples and potential. CES, just like I said, you could walk the floors and see all the individuals that are looking at new ways to interface with virtual and mixed reality systems. Also, as a neuroscientist, it's very interesting to consider AR and VR as modalities in which we can better understand brain function, and also develop new types of therapies and other types of medical applications. It was mentioned at one of the panels about neurofeedback and PTSD, so post-traumatic stress disorder, having some type of VR type of therapeutic that combined with a BCI system could help improve overall PTSD symptoms as well as quality of life. We're actually working with folks in Israel doing that exactly. And in fact, it has to do with regulating one's emotions. And I think also the economies of scale will make all this tech much cheaper. Really, an EEG system, at least, is not very expensive electronics. I mean, the ones that I show there, maybe they cost $100,000, but there's no reason they should cost that much. The electronics are relatively cheap. Miniaturization can really can make these things smaller and better. It's just the economies of scale. But what really needs to be done, at least to get kind of consumer grade systems out there, is the killer app. It's really something where you demonstrate that this type of channel, this type of interface, BCI, is going to do something that the consumer wants and can't do by pressing a button, interacting with a Leap controller, etc. Okay, so with that, I'll just acknowledge the collaborators, particularly the postdocs and students that contributed most to this. Dave Jangra, who's at NIH now, Joseph Fowler, who's in my lab, Samir Sapro, who's a CEO at one of the startups that came out of my lab, and Victor Shi, also a CTO at that. And then if you're interested in any more information, URLs, and also if you're interested in the brain and how IEEE is involved in the BRAIN initiative, please go to brain.ieee.org and join us as part of that community. Thanks.
Well, I think we have about 10 minutes, actually, for questions, don't we? Comments, questions, anyone? I guess maybe I'll throw one in there if my voice holds up. Excuse me. Your last slide said commercial killer apps with a quote sign around the killer apps. I was kind of thinking as you're talking about this that if the quote sign was moved in front of commercial, because one of the key things that people are trying to do is market research. Find out whether or not people are actually paying attention, audience measurement, are they actually looking at the TV? I know there's probably other ways to do it, but it seems like a lot of the underlying capabilities you were describing was the ability to see whether someone was paying attention, and you can pay people for the audience research and stuff. I don't know if that's something that people are looking at.
No, yeah, it's actually it's a pretty big or at least emerging area. It's the area of neuromarketing, and for instance, Nielsen, perhaps one of the biggest companies in this area, has bought companies that focus on BCI. I think what ends up happening is how do you demonstrate the value add, right? So in fact, I have one group that I've worked pretty closely with who does this trying to neural measures and neural ocular measures for monitoring engagement, whether it's in advertisements or movies, videos, what have you. And the interesting thing is once you start then getting to the community, so the marketing and advertising world is a very strange world. I don't know if you've all heard of that at all, but in many ways, it's the metrics on whether or not you were successful in using a new high-tech technique to monitor engagement, they're very far off and they're very subjective, right? So you can get ratings and things like that, but that doesn't usually tell the whole story. So a marketing executive or an advertising executive typically wants some kind of high-tech platform like this to basically just tell them that what they decided was the best thing anyway. So you've got, we actually did a study where you have a bunch of ads, and one ad is from the marketing company that made it, and there are these competitive ads, and then you rank them with a objective measure, and they just want to know that theirs came out on top or near top. So I think that how big that market is and whether that's the killer app, I'm not so sure. I actually think the killer app is going to be, at least initially, somewhere in gaming if it's done right, only because it's a natural place for VR and BCI, but I don't have it yet. So if anyone else does, good for you.
Another question here.
Hi. First, thank you for a very insightful presentation and talk. We heard last year an interesting keynote about the device. I forgot the name of the presenter, but it was about the headband. It's called Muse. Like a meditation device as one of the potential use cases. And my question is actually, because while I listened to you, you told us that sometimes the effect of neurological signal may be due to the eyes movement and not the brain. However, this concept with the headband seems pretty naive because you don't have like a full set of sensors out there. It's just a kind of a consumer thing. Does it actually work, in your opinion? And what is generally your take on that kind of use case?
So do you mean work? Does it record brain signals, or work, does it record something that could be useful? Right. Right. So I think that something like Muse is a nice product if your interest is in looking at physiological measures of the state of the individual. So like, but I don't think it measures brain activity. And the reason why has to do with the sensors, the quality of the sensors and the amplifier and their location, right? So it turns out if I have electrodes here, these are the electrodes that are most prone to artifact. And those artifacts, though, are correlated with things like stress. So for instance, how my eyes move is correlated with my stress level. Also, one of the strongest muscle artifacts in all of EEG is your forehead. And so when you get stressed, you tend to burrow your forehead, and therefore there's changes in the muscle activity that get picked up. So as a BCI, I'm skeptical. As a physiological measure that perhaps correlates with stress or so, it's very possible. And I think that the thing is, at some point, it doesn't matter if it's brain or not, if it does something useful, if it provides a measurement that is hard to get using like a camera or a joystick or a mouse.
Last question.
Yeah.
Hi, I came from the VR environment. I know very little about brain. But for years, the community in VR are trying to measure concepts like realism or presence. Do you believe that this brain signaling approach can help us measuring this kind of high-level cognitive concepts?
So using things like EEG, only if the experimental design is very well developed. So for instance, if you want to, in an environment, determine whether or not something is more or less realistic, you might see signatures of that in terms of